In this section, we will solve non-homogeneous linear second-order differential equations of the form ay double prime plus by prime plus cy equals f of t. Now, the non-homogeneous part of this expression, that just means that the function on the right-hand side is not equal to 0. So in the previous sections, the right-hand side was 0, and that is called a homogeneous linear second-order differential equation. Now, our experience from the previous sections lead us to believe that there will be an infinite number of solutions to this differential equation. Recall that in the previous section, when this was 0 and we did not have initial conditions, we had infinitely many solutions. Now, for now, we will be content with finding just one particular solution, and then we'll worry about other solutions if there are any later on. So in example 1, we're going to find a particular solution to the differential equation y double prime plus 3y prime plus 2y equals 3t. And the way we're going to do that is by taking an educated guess. So we're going to try and see, or we're going to try yp of t equals a times t. So our educated guess is that our particular solution will look something like the function on the right. So if we have yp of t equals a times t, then the derivative, we're going to need that, of yp prime of t is just a constant a, and the second derivative, yp double prime of t, is going to be 0. Okay, so now let's take our differential equation for yp double prime plus 3 yp prime plus 2 yp, that should equal 3t. And we're going to have to verify that. So now yp double prime is 0, and we had yp prime, that is a, and we had yp is a times t. So we have 0 plus 3a plus 2at has to equal 3t. Okay, now what we need to keep in mind is that when you have a differential equation, it has to be true for all values of the independent variable. So what we can do is we can bring the 3t to the other side, and let's just keep the 3a here. So now we have 2a minus 3 in between parentheses times t, and then plus 3a equals 0. Now a is a constant, and this has to be true for every t. So the only way that can be is if this coefficient is 0. This has to be 0. So therefore, we know that 2a minus 3 equals 0, or a equals 3 over 2. But once that is 0, then we have left that 3a equals 0. So from this, it follows that 3a equals 0. And that means that a is 0. Now, this is a contradiction. This cannot happen at the same time. So our try did not work. So a of t, or a times t, yp of t equals at is not a solution. Okay, now we're not going to give up just yet. Let's introduce a function that is slightly more complicated, but not too much. So our second try number 2, we're going to try yp of t equals at plus b. If we try that, then yp prime of t is going to be a, and yp double prime of t is still going to be 0. So now let's plug that in. And let's check and see if we can make that work. So it's yp double prime plus 3yp prime plus 2yp. That equals 3t. And now we're going to plug in what we know. Yp double prime is 0. Yp prime, that's a. And then we have 2yp, so we're going to have at plus b times 2. So 0 plus 3a plus 2 times at plus b equals 3t. Okay, now let's clean this up a little bit. So we're going to have 3a plus 2at plus 2b equals 3t. Now let's bring this to the other side. And we're left with 2a minus 3 in parentheses times t plus 3a plus 2b equals 0. Okay, now this has to hold for all t. So just as before, we now have that. Let's do it in a different color here. We have to have that 2a minus 3 has to equal 0. And that will make this 0 for any t. And then this has to be 0. So now we have a system of two unknowns. 2a minus 3 equals 0. And then we have to have 3a plus 2b equals 0. Now that first equation we can solve for a directly. So a is 3 over 2. And then the second equation turns into 3 times 3 over 2 equals, plus 2b equals 0. And so this is 9 over 2. Bring that to the other side. We get 2b equals negative 9 over 2, and then b equals negative 9 over 4. And that works out. So what we have found here is that yp of t equals at plus b works, and in fact it works with these two values. So our particular solution that works is 3 over 2t minus 9 over 4. So now the question is, can we generalize what we just did? And the answer is yes. We'll have to look at a couple of special cases. In general, a particular solution to ay double prime plus by prime plus cy equals c times some power of t is given by yp of t equals, and then it's going to look like this, some kind of constant a sub m times t to the power m plus a constant a m minus 1 t to the power m minus 1 plus etc., all the way down to the linear term a1t and then the constant term plus a naught. So if we see a power of t with a constant to a certain power, then we have to look at all, or our particular solution is basically any polynomial of that degree. So these values right here, the a sub m, the a m minus 1, the a1, the a naught, all of them are called undetermined coefficients. So we don't know ahead of time what they are, and so we have to determine them by plugging in this particular solution into the differential equation and then basically setting all the coefficients equal to 0 like we did over here. So that in general will give us m plus 1 linear equations in m plus 1 unknowns, and then by solving this system of equations we can then determine the values of a sub 0 or a naught, a1 up to a sub m, and then find a particular solution. And this technique is called the method of undetermined coefficients.